Hello everyone, in this lecture we will learn about the spectral representation of angle modulation and how it is mathematically represented. This lecture will be divided into two parts. In the first part we will derive the angle modulated signal ST and explore how it can be expressed using the Fourier series expansion. In the second part we will focus on the Bessel function of first kind J and beta, which determines the amplitude of the carrier and sidebands in the angle modulation. By the end of this lecture, we will have a clear understanding of the spectral representation of angle modulation and how the Bessel function helps to describe its spectrum. So let's get started. In this lecture, we will explore the spectrum analysis of angle modulation, particularly frequency modulation and phase modulation. Due to the inherent nonlinearity of angle modulation, the spectrum analysis becomes more complex compared to the amplitude modulation. We will begin with a singleton modulating signal and extend our understanding to more general cases. Angle modulated signal ST can be written as ST is equal to AC cos 2 pi FCT plus Kp into Mt for phase modulation. Identify this as equation number 1 and St is equal to AC cos 2 pi FCT 2 pi Kf integration from 0 to T m tau d tau for frequency modulation. Identify this as equation number 2 where AC is the carrier amplitude, Fc is the carrier frequency, Mt is the modulating signal or message signal, Kp is the phase sensitivity constant for Pm and Kf is the frequency sensitivity constant for Fm. And for instantaneous phase deviation phi t, for phase modulation Pm, phi t is equal to Kp into Mt, and for frequency modulation or Fm, phi t is equal to 2 pi Kf integration from 0 to T m tau d tau. Now we will consider a modulating signal applicable to both frequency and phase modulation and derive an unified representation of instantaneous phase deviation phi t within the general form of the angle modulation St. For frequency modulation, message signal or modulating signal Mt is equal to Am cos 2 pi Fmt, and the instantaneous deviation for frequency modulation or phi t is equal to 2 pi Kf integration from 0 to T m tau d tau, and we can replace this m tau as Am cos 2 pi Fm tau, and by performing the integration, this phi t can be written as Am into Kf divided by Fm sin 2 pi Fmt. Identify this as equation number 3. Now we can define the modulation index beta f for the frequency modulation as beta f is equal to Am into Kf divided by Fm, where Am into Kf represents the peak frequency deviation, Fm is the modulating signal frequency. For phase modulation, let modulating signal or message signal Mt is equal to Am sin 2 pi Fmt, and the instantaneous deviation phi t is equal to Kp into Mt, which is equal to Kp into Am sin 2 pi Fmt. Identify this as equation number 4. Now we can define the modulation index beta p is equal to Kp into Am. Here Kp represents the phase deviation per unit amplitude of the modulating signal and Am is the peak amplitude of the modulating signal. Now let's see the unified representation for both Fm and Pm. Now that we have already derived the expression for the modulation indices beta f and beta p, we will attempt to generalize them, and to achieve this we will choose the message signal in such a way that the expression for the instantaneous phase deviation or phi t becomes same for both phase modulation and frequency modulation. For frequency modulation, we can write beta is equal to beta f, which is equal to Am into Kf divided by Fm, and Mt is equal to Am cos 2 pi Fmt. So phi t is equal to Am into Kf divided by Fm sin 2 pi Fmt, or which can be written as beta into sin 2 pi Fmt. For Pm, beta is equal to beta p, Kp into Am, and Mt is equal to Am sin 2 pi Fmt. So phi t is equal to Kp into Am sin 2 pi Fmt or beta sin 2 pi Fmt. So the instantaneous phase deviation phi t has the value beta sin 2 pi Fmt for both frequency modulation and phase modulation. Thus, both frequency modulation and phase modulation can be analyzed under a common framework, making it easier to derive their spectral characteristics. Now we know that modulating signal St is equal to AC cos omega Ct plus phi t. Identify this as equation number 5. For a unified representation phase modulation Pm and frequency modulation Fm, we define this phi t as beta p sin 2 pi Fmt. Thus the angle modulated signal can be written as St is equal to AC cos omega Ct plus beta sin 2 pi Fmt. We can write omega c as 2 pi fc, so st can be written as st is equal to AC cos 2 pi fct plus beta sin 2 pi fmt. Using the Euler's identity, we can express this angle modulated signal in its complex form as st is equal to ac into real part of e to the power j beta sine 2 pi fmt into e to the power j 2 pi fct as the real part of e to the power j 2 pi fct into e to the power j beta sine 2 pi fmt gives cos 2 pi fct plus beta sine 2 pi fmt. Now we can express this e to the power j beta sine 2 pi fmt as s tilde of t, then st will become ac into real part of s tilde of t into e to the power j 2 pi fct. Identify this as equation number 6. So s tilde of t is equal to e to the power j beta sine 2 pi fmt. Identify this as equation number 7. This s tilde of t is a periodic with the period t is equal to 1 by fm. We can verify this property by shifting the time of this s tilde of t by k by fm for some integer k. So we can replace the time t of this s tilde of t with t plus k by fm, and we can write this as s tilde of t is equal to e to the power j beta sine 2 pi fm into t plus k by fm. If we multiply 2 pi fm with both the terms, then it will become e to the power j beta sine 2 pi fmt plus 2k pi. As k is integer, this can be written as e to the power j beta sine 2 pi fmt. So this e to the power j beta sine 2 pi fmt is periodic function of the time t, and it has a period of t is equal to 1 by fm. As this e to the power j beta sine 2 pi fmt is a periodic function with the period t is equal to 1 by fm, this allows us to expand it in a Fourier series. Or as the function is periodic, it can be expanded as a Fourier series, and the expansion will be valid for all the time. So s tilde of t can be written as if summation from n is equal to minus infinity to infinity cn e to the power j 2 pi n fmt. Identify this as equation number 9, where the complex Fourier coefficient c and are given by cn is equal to fm integration from minus 1 by 2 fm to 1 by 2 fm s tilde of t e to the power minus j 2 pi n fmt into dt. Here we can put the value of s tilde of t as e to the power j beta sine 2 pi fmt. Then the expression of complex Fourier coefficient can be written as cn is equal to fm integration from minus 1 by 2 fm to 1 by 2 fm e to the power j beta sine 2 pi fmt minus j 2 pi n fmt into dt. Identify this as equation number 10. Now we define the new variable x equal to 2 pi fmt, so that dt becomes dt is equal to 1 by 2 pi fm into dx. When t is equal to minus 1 by 2 pi fm, then x becomes 2 pi fm into minus 1 by 2 fm, which is equal to minus pi. When t is equal to 1 by 2 fm, x equal to 2 pi fm into 1 by 2 fm or pi. Now if we put the value of dt and the limits of t in the equation number 10, we can redefine the complex Fourier coefficient as cn is equal to 1 by twice pi integration from minus pi to pi e to the power j beta sine x minus j n x into dx. The integral on the right hand side is referred to as the nth order Bessel function of the first kind and argument beta. This function is commonly defined by the symbol j and beta. So the integral known as the nth order Bessel function of the first kind can be given by j and beta is equal to 1 by twice pi integration from minus pi to pi e to the power j beta sine x minus j n x into dx. Based on this, the complex Fourier coefficient can be written as cn is equal to j n beta, and by putting this expression we can write s tilde of t as summation from minus infinity n equal to minus infinity to infinity j n beta e to the power j twice pi n fmt. Identify this as equation number 11. Now we can substitute the value of s tilde of t in the equation of the angle modulated signal st. Then st can be written as st is equal to ac into real part of summation from n equal to minus infinity to infinity j n beta e to the power j 2 pi n fmt into e to the power j 2 pi fct, which can be further simplified as st is equal to ac into real part of summation from minus infinity to infinity j n beta e to the power j n 2 pi fc plus nfm into t. We can write this in more simplified form as st is equal to AC summation from n equal to minus infinity to infinity j and beta cos 2 pi fc plus n fm into t. Identify this as equation number 12. This equation 12 enables us to explain the angle modulated signal ST in terms of carrier and sideband frequency components. The carrier component is given by AC J0 beta cos 2 pi fct corresponding to n equal to 0. The upper sideband frequency components with the frequency fc plus fm, fc plus 2 fm and fc plus 3 fm are obtained by putting n equal to 1, 2, 3, so on. The lower sideband frequencies having the frequency fc minus fm, fc minus 2 fm and fc minus 3 fm are obtained by putting n equal to minus 1, minus 2, minus 3, so on. Thus, even for the simple case of singleton modulating signal, the angle modulated signal actually has an infinite number of side frequency components and an infinite bandwidth. However, fortunately, it is possible to define what is called an effective bandwidth, which is finite. This is because for any beta, j and beta tends to 0 as n tends to infinity, making the amplitudes of higher sideband frequency components negligibly small. So, the amplitude of the higher sideband components and the lower sideband components depends entirely on the nth order Bessel function or j and beta, which we will discuss in the next lecture. And this is the spectral representation of the angle modulated signal ST. We will see more about the amplitude and the carrier sidebands in the next lecture. So that's all for this lecture. In the next lecture, we will continue from here and understand the effects of the nth order Bessel function or j and beta in the spectrum of the angle modulated signal. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section and don't forget to hit the subscribe button. See you in the next one.